All right, let's get right into it. Welcome to this explainer, where today we are going to look under the hood of machine learning. We hear all the time about how AI models are trained on massive amounts of data, right? But how do we actually know they're learning anything real? Today, we're going to demystify the deep theory behind this whole process. We are getting into the mathematical guarantees of AI learning.
So here's the real puzzle we're trying to solve. We know AI works pretty well on the data it has already seen. It's training data. But out in the wild, the real world is completely unpredictable. So how do we mathematically prove that a model is going to work on brand new, unseen data? How do we know for absolutely sure it isn't just regurgitating a memorized answer key? Well, that right there is the fundamental, high-stakes question of learning theory.
To figure this out, here is our roadmap for today. We'll start with number 1, the Bias-Variance Trade-off. Then we'll look at the mystery of generalization. After that, we're bringing in 2 mathematical magic tools, applying them to guarantees for finite models, and finally, we'll tackle infinite models and the VC dimension. Let's hit it.
Section 1. The Bias-Variance Trade-off.
Think about a totally everyday problem that can completely ruin an AI's ability to operate in the real world. Let's say we're trying to predict housing prices based on the living area. On the one hand, we could have a model with large bias, or underfitting. It's just a simple, straight line. But housing prices aren't a perfectly straight line. They curve, they plateau. This simple model just completely misses the true structure of the data. Now, on the flip side, we have large variance, or overfitting. Here we're using a highly complex fifth-order polynomial. It twists and turns and hits every single training data point perfectly. But the problem is, it's memorizing spurious patterns. Maybe one house was unusually cheap because, it had a leaky roof and a family of raccoons living in the attic. If we use this hypersensitive, squiggly line on new houses, it's going to make wildly inaccurate predictions. Both of these extremes fail us in the real world.
Moving right along to Section 2, the mystery of generalization.
First things first, what is an AI actually doing when it's training? It's doing something called empirical risk minimization, or ERM. That's really just a fancy way of saying the algorithm looks at the training data, tests out a bunch of different parameters, and just picks the ones that make the fewest mistakes on that specific dataset. ERM is the most basic, foundational learning algorithm there is, and it's exactly what we're going to ground our mathematical proofs on today.
So the crucial point here is understanding the difference between 2 key metrics. Training error is basically just the fraction of examples the model got wrong during its practice test. It's super easy to calculate. But the generalization error, now that is the ultimate prize. If we're talking about a self-driving car, generalization error is the probability it makes a fatal mistake on a new street it's never driven before. ERM minimizes training error. But as we saw with that squiggly housing price line, acing the practice test absolutely does not guarantee a low generalization error in the real world. We need a bridge between the two.
Section 3. 2 mathematical magic tools.
Tool number 1 is the union bound. Honestly, it sounds almost like common sense, but it is incredibly powerful. It basically states that the probability of at least one out of a set of events happening is at most the sum of their individual probabilities. So if there's a 10% chance it rains and a 10% chance it snows, the chance it does either is at most 20%. In our analysis, this lets us group all the possible models our AI algorithm might pick from and put a hard ceiling on the chance that any of them are drastically failing us.
Tool number 2 is the Hoeffding Inequality. Now, we're skipping all the dense Greek letters here, but the intuition is beautiful. It elegantly proves that if your sample size is large enough, the probability of your empirical estimate being very far off from the true underlying reality is incredibly small. Basically, the larger your sample, the tighter your estimate hugs the absolute truth.
To really lock in this Hoeffding inequality concept, think about a simple coin toss. Imagine you have a coin, but you have no idea if it's perfectly fair. Maybe it lands on heads 60% of the time. If you flip it just twice, you might get 2 tails, which would be a terrible estimate of the truth. But if you flip that exact same coin 10,000 times, the fraction of heads you observe is going to be incredibly close to that true 60% probability. And this is exactly how training error works. Every single piece of training data is a coin flip. If you have enough training examples, your model's training error becomes an incredibly reliable estimate of its true generalization error.
Section 4. Guarantees for finite models.
Okay, let's look at how these pieces lock together to give us an actual mathematical guarantee. We've got 3 specific quantities here. We have m, the number of training examples. We have gamma, which is the error margin we're willing to accept between our training performance and our real-world performance. And then we have delta, our accepted chance of total failure, because hey,
In probability, there's always a tiny chance you just get a freakishly weird batch of data. Learning theory asks, how do these three balance out? If I want a tighter error margin, how much more data do I actually need?
And bam, here is the resulting formula that gives us our guarantee. To ensure our training error is a faithful representation of our generalization error, the number of examples m has to be greater than or equal to this equation. Now don't get bogged down in all the math here, just focus on that log k part. K is the number of possible models or hypotheses the AI is choosing from. The amount of data you need only grows logarithmically with k. This is staggering. It means you can exponentially increase the complexity of your finite model, and you only need a tiny, steady trickle of extra training data to maintain your mathematical guarantee of learning. It's ridiculously efficient.
Finally, Section 5, Infinite Models and VC Dimension. Here's the catch. Most modern AI models, like deep neural networks, use continuous real numbers for their parameters. That literally means they have an infinite number of possible functions. So how do we deal with that? Well, there's a clever, if slightly unsatisfying hack. We could argue that computers themselves aren't actually infinite. A computer stores parameters using 64-bit floating point numbers. So a model with d parameters actually only has 2 to the power of 64 times d possible states. It's finite. If you plug that massive number into our previous formula, the math works out to say the data you need grows linearly with the number of parameters. It's a neat little trick, and the conclusion is roughly correct, but is completely relying on computer hardware limits, not pure, beautiful mathematics. We really need a more elegant way to measure the true complexity of an infinite model. Enter the concept of shattering. Picture a 2D space. Step 1. Place 3 points anywhere, as long as they aren't in a perfectly straight line. Step 2. Assign them any combination of labels, let's say positive or negative, red or blue. There are 8 possible ways to label those 3 points. Step 3. Try to draw a single straight line that perfectly separates the reds from the blues. Well, it turns out, for all 8 combinations, a straight line can easily separate them. Because the linear model can perfectly handle every single possible configuration of those 3 points, we say the linear model shatters those points. But toss in a 4th point, a straight line just can't shatter every combination anymore. Which brings us to the ultimate investigative tool, the Vapnik-Chervonenkis, or VC, dimension. The VC dimension is simply the size of the largest set of points that a model can completely shatter. For our 2D linear model, because it can shatter 3 points but completely fails on 4, its VC dimension is exactly 3. We finally have a single, finite integer that perfectly captures the complexity or flexibility of an infinite model class, and we didn't even need any 64-bit hardware hacks to get there.
And that brings us to the grand finale theorem of learning theory. Once you know the VC dimension of a model, you can mathematically prove its generalization error. This corollary states that the number of training examples needed to guarantee an AI learns effectively is roughly linear in its VC dimension. Because the VC dimension is generally proportional to the number of parameters in the model, this is it. This gives us our definitive proof. Even with an infinite number of possible functions, as long as the model has a finite VC dimension and we feed it enough data, the model absolutely will learn the underlying truth. It is not just memorizing. This is exactly why we can trust neural networks to recognize speech or diagnose diseases. Case closed.
So, we did it. We walked through the math, we've seen how the union bound, Hoeffding's inequality, and the sheer genius of the VC dimension all lock together to mathematically guarantee that learning is possible. But I want to leave you with a bit of a provocative thought here. If the fundamental theory mathematically guarantees learning when given enough data, what is actually limiting the AI of tomorrow? Is it really just a matter of gathering more data? Is it sheer compute power? Or are there hidden complexities in these massive deep neural networks that are going to require an entirely new kind of math? It's definitely something to chew on. Thanks for joining me on this explainer, and keep exploring.